All right, let's jump right into this explainer. Today, we're taking a seriously incredible journey. We hear a lot about the AI revolution, right? We talk about the massive language models, the microscopic chips, but we rarely talk about the massive physical infrastructure actually required to power the whole shebang. We're hitting a literal physical wall where our AI ambitions are colliding head-on with the very real limits of our planet's power grids and water supplies. So we're going to look at some of the most extreme, elegant engineering solutions happening right now to fix this bottleneck. We're going from the bottom of the ocean to the freezing Arctic and all the way up into the vacuum of space. To really grasp the scale of this, we kind of have to rethink what a data center actually is. NVIDIA's CEO Jensen Huang hit the nail on the head when he compared the modern AI data center to the invention of the electrical dynamo. But, okay, instead of taking in coal or wind and outputting electricity, this new dynamo takes in raw electricity and literally manufactures intelligence. We're no longer just storing your old smartphone photos or hosting websites. We're building massive factories. And the scale of energy these factories demand, it is unlike anything humanity has ever seen.
And this skyrocketing demand, it's being driven by what's called the agent-tech economy. Think about it. We are on the verge of introducing billions of digital workers, these AI agents, into the global workforce. And these aren't just your standard software programs. They're autonomous thinkers. They're solving problems, coding, creating. And here's the kicker. These billions of new digital employees don't buy houses and they don't eat food. They only consume one physical thing to survive, and that's compute. So the total addressable market for intelligence is no longer capped by the human population. It's essentially infinite.
Which leads us to a pretty shocking reality. By 2028, it's projected that terrestrial data centers could consume up to 12% of the entire United States electricity grid. 12%. That is absolutely massive. We are quite literally in a race between the exponential growth of intelligence and the physical limits of our energy infrastructure. The bottleneck isn't the software anymore, it's the physical world. That 12% represents power competing directly with your local hospitals, schools, and homes. And it gets crazier. To keep those AI chips from melting down, traditional land-based data centers evaporate a staggering 1 to 9 liters of fresh water for every single kilowatt-hour of energy they use. They're essentially fighting against physics, using these brute force mechanical chillers and evaporative cooling towers that put an immense strain on local watersheds. But there is a better way. The computing industry is realizing that to survive, it has to go off-grid. We need to seek out environments where we can actually work with thermodynamics, targeting zero water consumption.
So, Section 1, Ocean Compute and Project Natick. To solve this water problem, we're leaving the strained terrestrial grids behind and heading straight to the bottom of the North Sea.
Look, since 50% of humans live near the coast, why doesn't our data? Microsoft actually engineered a massive pressure vessel for this. They packed it with 864 servers, replaced all the oxygen inside with dry nitrogen, and deployed it 117 feet deep on the Scottish seafloor, all in under 90 days. It uses submarine heat exchange tech, basically pulling that freezing ocean water right across the racks. The result? Zero fresh water evaporated, none. And the results from this are just staggering. When they pulled the data center up after 2 years underwater, they found it had 1/8 the failure rate of a comparable land-based facility. Why? Well, because without humans walking around bumping into racks and without all that corrosive oxygen degrading the components, the hardware absolutely thrived. It proved that fully automated, off-grid compute isn't just some fun sci-fi experiment. It's actually vastly more reliable.
Moving on to Section 2, Arctic Arbitrage. This is where we get into this really icy Nordic solarpunk aesthetic. Let's move from the Scottish coast to the frozen Nordic Arctic, where a truly beautiful, visually striking concept is coming to life. We're talking about something called geothermal arbitrage. Instead of building data centers in hot climates where they have to constantly fight the environment, operators are placing them up in the freezing Nordic countries. Up there, they can utilize continuous free cooling. But it goes a step further, and this is the really cool part. In true solarpunk fashion, rather than just venting all that massive server heat out into the sky and wasting it, these facilities capture it. They then seamlessly route it directly back into the local municipal infrastructure. Just compare traditional cooling, which literally guzzles tens of millions of liters of water, to this Arctic free cooling. By utilizing a closed-loop system that just channels the naturally freezing outside air to cool the servers, a 10-megawatt facility in Finland uses just 10 to 20 cubic meters of water a year. Guys, that is an unbelievable 99% reduction. It's an absolute game changer. It is a complete paradigm shift in how we handle the intense thermal load of artificial intelligence.
So, the intense waste heat generated from an AI answering your trivia question or drafting an email, it's captured by giant heat pumps and injected right into the municipal networks. It's warming Finnish homes, local fish farms, and community greenhouses right in the dead of winter. So yes, an AI drafting your Tuesday meeting agenda is quite literally keeping a Finnish fish perfectly warm. This is exactly what we mean by sleek, high-end technology, harmoniously blending with and actively supporting thriving local communities. All right, Section 3, the Space Compute Frontier Orbital Infrastructure. Let's pivot from the harmonious Arctic to literally the most hostile off-grid boundary imaginable: space. With mounting pushback against data centers here on Earth, the space industry is pitching a pretty enticing idea: abundant solar energy, absolutely no zoning battles, and no grid queues. And you might immediately think, well, space is freezing cold, so cooling those hot AI chips up there will be incredibly easy, right? Why not just put them all in the freezing vacuum of space? But here is a totally counterintuitive physics reality check. The vacuum of space is actually a near-perfect insulator. Down here, we use air or water to cool things by transferring heat. Up there, there's neither. So the immense heat from the chips just gets trapped. According to the Stefan Boltzmann law, the only way heat escapes a vacuum is by radiating away as invisible infrared light. That means it completely, 100%, relies on the surface area of your radiator, which creates a brutal engineering bottleneck. Get this: to cool just a tiny 1 megawatt space data center, just keeping the chips from melting at around 20 degrees Celsius, you need a radiator surface area of roughly 1,200 square meters. That is the size of an entire ice hockey rink, or 4 tennis courts, just to cool a single megawatt of compute. As you can imagine, the mass and cost of launching radiators that huge is astronomical. But this crazy bottleneck is sparking some unbelievable sci-fi level innovation right now. StarCloud is launching these modular hyperclusters with massive deployable radiators. Axiom Space is testing specialized thermal tiles to reject heat directly into the cosmic microwave background. Sophia Space is designing a swarm of small satellites. Picture them like silver dragonflies, using their entire outer shells as passive radiators. And incredibly, Lone Star is actually looking at placing servers inside subterranean lunar lava tubes. They're completely bypassing the radiator issue by using the moon's own thermal mass as a natural heat sink. Just wild stuff. Section 4, the future of intelligence and physical infrastructure. Let's bring this journey back down to Earth for a second. What does this massive engineering race actually mean for the future of our physical infrastructure? Well, we're making unbelievable thermodynamic strides. Look at power usage effectiveness, or PUE. It's a metric where a score of 1.0 is mathematically perfect. We're seeing subsea environments hit 1.07 with zero water usage. Arctic free cooling is hitting 1.12 using just fractions of a liter. Geothermal storage hitting 1.03. We are proving right now that elegant efficiency is entirely possible. We don't have to drain our rivers or our power grids. We just have to work with physics instead of constantly fighting against it. Which leaves us with this final, really provocative thought. As the investor Jordi Visser noted, if the universe is ultimately solving for intelligence per unit of energy, capital and human innovation are going to relentlessly clear every single roadblock to get there. Whether it's beneath the ocean waves, warming a community greenhouse in the freezing Finnish Arctic, or nestled deep inside a lava tube on the moon, we will find a home for the billions of AI agents waiting to be born. So the question isn't really if we'll build this massive infrastructure, but how elegantly we can weave it into the fabric of our world. Thank you so much for joining me on this explainer.